Okay, let's go over the review of Unit 3C, Learning Target 16 through 22. Apologize for my voice. I'm just getting over the flu or something. So hopefully you can hear me okay. All right, number 1. Does this molecule follow the Honk 1, 2, 3, 4 rule? Well, no, it doesn't, because this carbon has only 3 bonds. And it should have 4 because it's Honk 1, 2, 3. Carbon has 4. All the other carbons have 4, so that's good. Next, let's check the hydrogens. Yes, all the hydrogens have 1 bond. Oxygen, only 1 bond. And it should have 2. And nitrogen is supposed to have 3, but it only has 2. And so that is not okay also. So there's quite a few things wrong with that. Are these molecules isomers? Well, let's see, it goes carbon, carbon, oxygen, carbon, carbon, oxygen. So no, they are exactly the same. Just rotated 180 degrees in 3 dimensions. Draw 2 isomers of C3H9NO. Don't worry about lone pairs for this one. Just be sure it follows Honk 1, 2, 3, 4. Okay. I'm going to do one where I just put them all in that order. And carbon gets 4 things. So that needs 2 more hydrogens. This one needs 2 more. Nitrogen needs 1 more thing. That follows Honk 1, 2, 3, 4. And then I could do C, C, C. I could put the N off. I could put the O going up. It's still 9 hydrogens. And these are very different arrangements. You can even see this one is like more spherical. This one is more linear. Draw a Lewis dot structure for selenium. Well, if I check the periodic table, I guess they're not off to the side on this one. Selenium is in group 6A. So it gets 6 dots. You go around clockwise. 1, 2, 3, 4, 5, 6. And so there's 2 places where it would like to form a bond because it has 2 lonely electrons. Next, draw a Lewis dot structure for each of the following and name the shape of each molecule. So we've got SCl2. I'm going to do S has 6 because it's in group 6A. I'm going to point the lonely electrons toward the chlorines. Chlorine has 7 because it's in group 7A. Boom, boom. This would be a bent shape because these lone pairs push down on those chlorines. Okay, C2H4. Carbon has 4 lonely electrons because it's in group 4A. Connect them once. Hydrogen has 1. I draw 2. And so then they're going to need to connect 1 more time. So if I redraw this nice and neat, carbon has a double bond between the 2 carbons there. What shape? There's actually 2 central atoms. Each of these has 3 things around them. and no lone pairs. So that would be trigonal planar times 2. pH3, P has 5 electrons, and each hydrogen has 1. So, boom, boom, boom. This has 3 things around it, excuse me, and 1 lone pair. So this would be trigonal pyramidal. That lone pair would push down on the other 3. CH3OH. Sorry, guys, about my voice. Boom. And then we've got 4 hydrogens. So this one is a tetrahedral. It's got 4 things around it. And this one has 2 things and 2 lone pairs. So it's bent. Last, we've got oxygen. Boom, boom. So if I'm redrawing that nice and neat, this would just be linear. Using a bent molecule below, explain the role of electrons in determining a molecule's shape. Electrons repel each other. So this molecule is bent in 3 dimensions. Each bond angle is 109.5 degrees. So if I were to draw this like, let's see, I'm going away. You can see if you just focus on the HOH, H2O, that it would be in a bent shape. Define electronegativity. It's the ability of a bonded atom to attract electrons to itself. And polarity is a molecule with a partial positively charged end and a partial negatively charged end. Draw a Lewis dot structure for SF2 and label it as polar or nonpolar, if appropriate. Draw the dipole arrows and label the partial positive and partial negative charges. Okay. S is in group 6A. It's got 6 dots. F is in group 7A. It's got 7 dots. Let's look up their electronegativities. Sulfur is 2.58, I believe. Fluorine, sorry, I should have connected these, is 3.98. So 3.98 minus 3.58, 1.40. So fluorine is the greedy, so you point arrows at the fluorine, which means fluorine gets a partial negative and sulfur gets a partial positive. So does this have a partial positively charged end? Yes. and a partial negatively charged end, yes. So this molecule would be polar. Okay, draw CH3F. Label it as polar or nonpolar. If appropriate, draw a dipole arrow and any partial charges. Okay. Carbon is 2.55. Fluorine is 3.98. Hydrogens are just 2.1. So there's only a 0.45 difference between them and the carbon. So that's not significant enough to be considered polar. But fluorine minus carbon is, because that difference is between 0.5 and 2.1. So fluorine is pulling. Fluorine gets a partial negative. Carbon gets a partial positive. And this is indeed polar. And then if we're going to draw two of these molecules aligning themselves, draw this a little better here. The partial negative would be attracted to the partial positive of another. So they would kind of line up where the carbon is as close as possible to the fluorine of the other. And let's figure out what the intermolecular force would be between them. So it's a polar molecule. So that automatically eliminates dispersion forces because that's only the strongest if it's between nonpolar. Now we ask ourselves, does it have an H connected to an F, an O, or an N directly? No, it has a C connected to an F. That means that it's going to have dipole intermolecular forces between the two. Also some dispersion, but they wouldn't be considered the strongest present. And this would not have hydrogen bonding forces. Last, which would be more likely to exist as a gas at room temperature? C2H6 or C2H5OH? Oh, let's talk about the first one. This has no greedy atoms. No greedy atoms. Carbon and hydrogen, it's just a tie. Remember, it's 2.55 for carbon's electronegativity minus hydrogen's 2.1. That's only a difference of 0.45. So what this means is this is nonpolar molecules here. And so the intermolecular force would be very weak. It would be dispersion forces. So they're only held weakly together. On the other hand, C2H5OH, this has a partial negative and some partial positives because this is a greedy atom. So the oxygen of one is maybe attracted to the positive of another nearby. In fact, pretty strongly attracted because we are going to see that these two polar molecules, they do have a hydrogen directly bonded to an H, which means that the intermolecular force between them is hydrogen bonding forces. So let's go back to the original question, because these guys are held together strongly. So which one would exist as a gas, meaning the molecules are just going to fly away from each other because they're only weakly held together? Answer, C2H6, because they have weak forces holding them together, so they can fly away as a gas. Hope that helps you. Sorry again about my voice.